This is the second part of this presentation on curve sketching. This is the function we're working with. F of x equals 1 over x minus 3, where x is not equal to 3. So we had a quick look at intercepts and stuff like that, and also a bit of curve sketching when we found the asymptotes. What we're going to do now is find the stationary points, the local max and the local min. Okay, local maximum, local minimum. Okay. Now, in this question, actually, we have to sort of these stationary points, local maximum, the local minimum, they don't always exist. Okay, so that's just bear that in mind. The general game plan, all the same, is that we get the derivative of the function, let it equal to 0, and solve. Okay, so here's our function, f of x equals 1 over x minus 3. Now, just to sort of be consistent, what we're going to do is that just rather than f of x, we'll just call that y. Okay, and what we're going to do is get the derivative of that. So y is x minus 3 to the power of minus 1. Okay, and we could just treat x minus 3 as if it was x when we differentiate it. And therefore, we would get minus 1 times x minus 3 to the power of minus 2. Or in other words, minus 1 over x minus 3 squared. Okay. So, again, just to be clear about this, when you're dealing with things like x minus 3, you can actually just treat it as if it was x. Okay? So, as if, just like as if it was x, just x minus 3, there's no real difference. Now, we're going to let this equal to 0, or can we let that equal to 0? So, is minus 1 over x minus 3 squared equal to 0? Now, this is the thing, actually, I sort of explained it before. If a over b is equal to 0, that means a has to be equal to 0. So, for this particular example, minus 1 has to equal to 0. No. Not going to happen. Okay? Doesn't work. That's wrong, basically. So dy over dx is can't ever equal to 0. Okay? That's it in a nutshell. I just got rid of that there, but we'll just draw that in again. So that's the thing, the gist of it there. Dy over dx, which is minus 1 over x minus 3 squared, that can't equal to 0. The reason is because if we have a fraction, for it to be equal to 0, the numerator has to equal to 0. And that's not the case here. So there are no turning points. Okay. There's no local max and no local min anywhere. Okay. Now, just as an extension of that, if we were asked points of inflection, what we would generally do there is get the second derivative and let that equal to 0. Now, in this case, what's going to happen here is same problem exists, that we will not be able to solve that because, which is end up with the same problem. We get a fraction, and the numerator would also have to necessarily be equal to 0, and that's going to be a case where it's going to be constant, which can't equal to 0. So that's the just general gist of it. Okay. Now, one more thing I'm going to do is let's go back here. F of x equal to 1 over x minus 3. Okay. So, in this case, what we have here is, what we are interested in here is the behavior as x approaches infinity and x approaches minus infinity. Now, this particular example is a little bit tricky because it doesn't really make for a good one. But in general, actually, what we just do is straightforward, treat them as a limit problem, simple limit problem. So as x approaches infinity, we have 1 over infinity minus 3. That's 0. That's 1 over infinity, 0. 1 over the limit as x approaches minus infinity. Again, minus infinity over minus 3. So minus infinity, well, we'd end up with minus 0 essentially, but that's just a 0. Okay. We always conserve the sign when we're dealing with the minus infinity. So that sign gets conserved, but minus 0 is just 0. Okay. But essentially what we do is just treat it like a straightforward, very simple limit problem where we just evaluate it at each point at minus infinity and infinity. So that is the stationary points and also the long-term behaviors. Okay.